Okay, so good evening, everyone. My name is Lorea Armendariz. I'm a product student at the University of Oxford, and I'm going to present this ongoing work that is entitled Development of a Hybrid High Entropy Alloy Steel to Mitigate Hydrogen Embrittlement. Okay, so the motivation of this work comes from developing new materials for hydrogen, and it is well known steels, especially high-strength steels, suffer from hydrogen embrittlement, and especially their mechanical properties are reduced with increasing hydrogen content. However, on the other hand, high entropy alloys, as we have seen before, are gaining attention because they have demonstrated a lower reduction of properties under certain hydrogen charging conditions. So the idea of this work is to create a combined material with steels and high entropy alloys with the purpose of combining the strength of the steels and these hydrogen properties, good hydrogen properties of the high entropy alloys, because high entropy alloys show lower mechanical strength. So we propose a multi-layer structure that can be resistant to hydrogen environments. And the idea is that the steel is going to be the core material, providing the structural strength. And the high entropy alloy with slow hydrogen diffusivity can delay the uptake of hydrogen to the steel and also provide a good corrosion resistance and hydrogen embrittlement resistance. So the first aim of this work is to study the microstructure and mechanical properties of this combined or hybrid material, and also characterize the interface between the high entropy alloy and the steel. And however, if we introduce hydrogen to this hybrid material and we think about the worst scenario, when the hydrogen diffuses through the high entropy alloy and reaches the interface there, we want to see what happens in this worst situation. So this is the second aim, study the role of this interface when the material is mostly full of hydrogen. So this hybrid material was fabricated through a near solidus forming technique. We have the raw materials, the equiatomic high entropy alloy, and then chromium nickel molybdenum steel in a scarce condition with the chemical composition shown in these tables. And then we preheat these two materials, reaching temperature close to the solidus point. And then we apply a load in order to join the two materials in this near solidus state and obtain this hybrid material with the high entropy alloy in the top and the steel below. So for the first aim, we did the microstructural analysis and the mechanical properties through tensile testing. And first of all, we cut the specimen in the middle, and we did a SEM micrograph to see how this interface and the two materials were looking. So performing EBSD analysis and X-ray diffraction, we saw that the high entropy alloy has FCC crystal structure with big grains here, as you can see in these figures. And then below the steel has a finer microstructure, martensitic and BCC. In the interface, we did some preliminary X-ray diffraction, and we didn't see any precipitation of additional phases. So we can, this is an ongoing work. We are analyzing these EBSD scans in the interface, but we can say that there is no precipitation of additional phases during the fabrication process. Then, to see the transition of the chemical composition across the interface, we perform EDX profile, and we can see here the equiatomic chemical composition of the high entropy alloy. And then, when we reach the interface, we have sudden increase of iron and a decrease of the other elements that is more progressive. And if we look in more detail in this interface, we can see that there is a region where we have element diffusion of around 10 microns. So we can say that the interface there is like a transition zone between the two materials. Then we did micro harness measurements also across the interface with different loads. And we saw that the high entropy alloy has an average harness of 180 beakers. Then in the interface, we have a sudden transition and an increase in harness, reaching about 350, 380 beaker harness for the martensitic still. Then, as we don't have good resolution here around the interface, we did nano harness measurements. And this is the nano harness contour map we obtained here in this area close to the interface. So here we can see some aligned with higher harness values that is located in the interface. And then we can see a transition between the low harness values here in the left and then high harness values in the right. So we can say that there is a transition in harness that more or less 40, 50 microns. So here we can see that the interface has like a transition in both chemical composition and harness. So for the mechanical properties, the question is how can we assess the mechanical properties of this hybrid material? So there are three possibilities for the tensile specimens. This is the first one, the second one, or the third one. So for our application or idea, or the point of view that is the high entropy alloy, the one is going to be in contact with the hydrogen and is going to diffuse this way, we started assessing this third configuration. So we extracted the specimens from the samples with these measures, and we obtained this is an example of one of the specimens, and then we reduced the thickness up to 1 millimeter, reaching like having a 40% of high entropy alloy and 60% of steel in all of the samples. So first we started analyzing the mechanical properties of each material separately, then to compare with the hybrid material. So for the steel, we obtained a yield strength of more or less 1,000 megapascals and an elongation of 9%. Then for the high entropy alloy, the behavior was completely different. The yield strength was 250 megapascals and an elongation of almost 40%. So for the hybrid material, we obtained the following results. And here we can see there are two experimental curves. So the scatter is very low. Both curves were similar. And the mechanical behavior is intermediate between the two materials. So we obtained yield strength of almost 600 and then an elongation of 10%. So we can say that we have obtained a material that is a little bit harder than the high entropy alloy and can provide this barrier for the diffusion of hydrogen. And then we did some theoretical approach following the rule of mixtures to see how were our results far from the theory. And we obtained this green curve with the rule of mixtures. So knowing that the rule of mixture has several assumptions that maybe considering an ideal coupling between the two materials, the stress are uniformly distributed, aligned orientations. So our samples are a little bit below because maybe the interface is not totally straight and maybe there are some little cracks that we don't see, but it's like similar. So then for the second part, we started with putting hydrogen into the samples. We did electrochemical hydrogen charging at 60 degrees. because the idea was to introduce hydrogen to the high entropy alloy, the hybrid and steel. So then after charging, we did slow strain rate tensile tests and thermal distortion spectroscopy to measure the hydrogen concentrations. So for the steel, after introducing hydrogen, 3 hours, because we did some simulation and was enough to saturate the sample, we obtained 0.24 weight ppm of hydrogen. And as you can see, there is a slight decrease of ultimate tensile strength. And then looking at the fracture surfaces, in the no hydrogen one, we can see the microvoids. And then in the hydrogen one, we can see like other flat areas apart from the microvoids. And the most noticeable parameter for the hydrogen embrittlement was the reduction in area that was reduced. Then for the high entropy alloy, after introducing hydrogen for 13 days, we saw that a hardening effect. Here, the yield strength was increased, and but the elongation was reduced, as well as the reduction in area. So we can say that the high entropy alloy suffer a little bit of embrittlement. And then looking at the fracture surfaces, we can see that with no hydrogen, there were some voids. And then for the hydrogen one, we saw a quasi-cleavage phase passage there. So that was the result after introducing 150 ppm of hydrogen. So for the hybrid material, you can see here in the micrographs, before introducing hydrogen, we have the two materials, the steel and the high entropy alloy, and there are microvoids in both, separated by this valley where along the interface here. And after introducing hydrogen for also 13 days, we can see a reduction of properties also. Okay, so what happens in the fracture surface after introducing hydrogen? So we went with more detail into this interface area, and we saw that the steel zone, some microvoids were observed. Then in the high entropy alloy, the quasi-cleavage zones were observed as in the previous high entropy alloy samples. But in the interface area, we saw some intergranular cracking there. The same was observed in the middle of the sample, here, and also in the other side of the sample. So these results suggest that the interface is trapping hydrogen, and the hydrogen that is at the interface is reducing the mechanical properties of the hybrid material, as we can see here in the hydrogen embrittlement indexes. So as a conclusion, we can say that the interface is a transition zone in terms of chemical composition and hardness of about 10 to 50 microns. Then the hybrid material shows intermediate mechanical properties with a higher tensile strength and a little bit higher ductility than the steel. And then the intergranular fracture was observed around the interface in the hydrogen charge specimens, suggesting that there is a higher hydrogen concentration there, and that the hydrogen embrittlement resistance of the hybrid alloy, once is mostly with hydrogen, is not improved with respect to the steel of the high entropy alloy. And some of the ongoing work that we are doing now is other tensile testing orientation that I have shown before to fully assess the structural integrity of this hybrid material. Then in situ hydrogen testing and EVSD characterization on the interface and the fracture surfaces, and TDS and gas permeation testing to see what's happening there in the interface and to have more information about hydrogen trapping and hydrogen diffusion. And finally, analyze the influence of the still high entropy ratio on these properties.